Okay, let us start. I'm very happy to have Salvatore Torquato from Princeton University. As you can see, quite a few departments of chemistry, physics, materials institute, and applied and computational mathematics. So Sal is a world expert on structure and transport in heterogeneous media, including then sphere packs and similar things. So, and he will tell us about that. No sense for me to waste time on it. So, in terms of history, he got his PhD at State University of New York with George Stell in 1981. So there our career sort of touched base as I came there 2 years later as a postdoc and had the pleasure of building on some of the foundations that Sal had laid in his PhD thesis. From there, he went to North Carolina State University as an assistant and an associate professor, and then on to Princeton in from 1992, and since 2018 he has the chair, Louise Bernard Professor in Natural Science position there. I think pretty much I'll stop there, Sal. I don't want to take any more of your time.
Thank you very much. I want to thank Per. Thank you, Per, so much for inviting me.
They are now recording.
Okay. I want to thank Per very much for inviting me to give this presentation. It's been a long time since Per and I have been able to actually see each other, so it's wonderful to see you, Per. I think it's a great opportunity to talk about some of these things. What I basically want to convey, just give you a big picture of what I want to convey, is that in terms of the fluid permeability, which is actually going to be central to this talk, one of the important things is we would like to be able to characterize the pore space and then use information about the pore structure to be able to predict the permeability. But you can do that in a number of different ways. And one way is to directly measure correlation functions of the pore space. Another way is actually to look at seemingly different properties of the porous medium, and then actually connect those seemingly different properties to the fluid permeability. So all of this is the permeability is central, but the foundation is what is going on in the pore space. How do we characterize it? And the permeability among all of the particular properties concerned is the most challenging one to predict from a theoretical point of view, and that's what I'm going to be talking about. Okay, for some reason this is not advancing. I don't know why. Okay, now it is. Okay. So to begin with, I'm going to be considering two-phase media just for simplicity. So I have a phase 1 with typically, I will call it volume fraction phi1 and some properties k1. And then I have a phase 2 depicted here as red particles, which will have a volume fraction phi2 and a set of properties k2. And the idea is that you have this macroscopically large system of length L, capital L, and you have a heterogeneity length scale, little l, which is much smaller than that, but much, much larger than atomic length scales. And so what you want to do is you want to replace this heterogeneous system with some effective homogeneous medium and ascribe to it an effective property. And of course, we know of many, many different examples of such heterogeneous media. You want to be able to then predict the effective properties, and the effective properties will be linked to information about the microstructure. Now I list a bunch of different properties here. This is actually a partial list. The ones that I highlight in red are the ones that I'm going to be focusing on during this talk. And in particular, the effective conductivity of this heterogeneous medium, as well as certain kinds of diffusion timescales. And let me tell you first about the mean survival time. This is actually related to NMR experiments, and many people, for example, at Schlumberger et al., did a lot of work much earlier concerning how you relate NMR timescales to the fluid permeability. So this is directly connected to that problem. And here what you have is, you imagine that this is the fluid phase, and you have some species diffusing within this fluid phase. And when it comes in contact with the interface, it gets trapped. So that's the end of that random walker. And you want to be able to predict the mean time, the mean survival time of Brownian particles that are released within this pore space. That's a steady state quantity, which I'll say more about later. And then there are relaxation times associated with the relaxation of diffusing particles as a time-dependent problem. So I will explain that as well later. Of course, everybody, I think, in this audience is going to be familiar with the fluid permeability tensor, which is going to be determined from Darcy's law. Okay. So the outline of the rest of the talk, I'll be talking about definitions of the statistical microstructural descriptors. Now, there's a concept that is very, very new, well, relatively speaking, new, that's called hyperuniformity, and it's a way of characterizing the large-scale structure of different systems that I want to say something about because it gives us insights into fluid permeability. And then the rest of the talk is going to be divided into two parts. One is going to be a recent paper that I wrote in Advances in Water Resources that involves microstructure-dependent estimates of transport properties. But ultimately, all of these, we want to be able to connect them to the fluid permeability. So I'll be talking about that. And then in the second part of the talk, there's an even more recent idea that I introduced called the diffusion spreadability. That is also a time-dependent diffusion problem. And it enables characterization of the pore space in a pretty interesting way that I think you'll see later. Okay. For those of you who are interested in machine learning type techniques for the fluid permeability, I'm not going to say really anything about this paper, but we use these kinds of microstructural quantities to be able to look at something like 30,000 data sets, and then ascertained from among the particular correlation functions, which ones are the most relevant to be able to determine the fluid permeability. And so I'm not going to say anything about that, but I thought maybe some people would be interested in that paper. Okay, so let's begin with the statistical descriptors of two-phase media. So I have a two-phase medium. Now I'm speaking a little more generally than just porous media. So a two-phase medium in d-dimensional, so that's my notation for d-dimensional Euclidean space, is fully statistically characterized by the endpoint correlation functions, which is this quantity here. What is this? Well, you take the ensemble average of the so-called indicator functions. It's a function, it's a random variable that is 1 in phase I and 0 otherwise. And if you take the ensemble average of a product of these, that gives you this endpoint correlation function. Now, it turns out that this is also probabilistically the probability of finding endpoints at these positions in one of the phases, say phase I. Now, if the system is translationally invariant, in other words, it's statistically homogeneous, then these quantities only depend upon the relative displacements, not the absolute positions of x1 to xn. And in particular, in the 1-point case, S1 is simply the volume fraction of phase I. Another important quantity is the specific surface, and you can define indicator functions for the interface, as it turns out, which is going to be the absolute value of the gradient of this indicator function. So you can think of this as a generalized function. So this would involve Dirac-like functions. And if you take the ensemble average of that, that gives you the specific surface, okay, the interface surface area per unit volume. And then you can define all kinds of higher order versions of the surface correlation functions that I will not have time to describe. Okay, now let's talk about quantities at the 2-point level. So if you take this 2-point correlation function, and let's consider, it doesn't matter whether it's phase I or phase II, if you subtract the long range value of S2, which is phi1 squared, and then in the case of the phase II, it would be phi2 squared, those are exactly the same, and we're going to call that the autocovariance function. So if you have a disordered system, this function will tend to 0 rather rapidly, okay, for large R. Now, if you take the Fourier transform of this quantity, you get the spectral density at a wave vector k. And this can be obtained from scattering experiments. So you might be familiar with very well-known papers from the 50s by Debye, where they were doing small angle scattering. And this is exactly the quantity that you would get from small angle scattering. In the large K limit, this quantity, the spectral density, decays like a power law, inverse power law, with a coefficient that is proportional to the specific surface. Okay, now another very interesting quantity when it comes to porous media is the local volume fraction variance. So imagine that I have a spherical window of radius capital R, and I count the volume fraction within that window. But if I locate it at a different place, the volume fraction will be different. So I have a random variable associated with the volume fraction. And I'm going to call the variance for that particular radius R, I'm going to call it sigma v squared. And you can show that that variance, that local volume fraction variance, is an integral that involves either the haute covariance, if you look at the direct space representation, and a purely geometric quantity, which is essentially the volume common to two spherical windows separated by a distance little r. So this is the direct space representation. And then there's a Fourier representation, which involves the spectral density associated with this variance, autocovariance, as well as the Fourier transform of this intersection volume, okay? Now, most of the time I'll be talking about things in Fourier space, so this is why I mentioned the spectral density in particular here. Some other very important descriptors when it comes to porous media is what I call the pore size probability density function. So this is the probability that a randomly chosen point in the pore space lies at a distance between delta and delta plus d delta from the nearest point on the pore solid interface. Now, at the extreme values of this quantity, at 0, it gives the specific surface divided by the porosity. And at infinity, it must be 0. And then we're interested in the moments of this probability density function. So this is the nth moment. And very specifically, we're going to be applying the first moment, which I'm going to call the mean pore size, as well as the second moment. And these are going to be important characteristic length scales of the pore space. And we're going to show that these characteristic length scales are going to be related to diffusion properties. The other thing I want to point out is that the pore size probability density function can easily be extracted from 3D digitized images of real porous media. And for that, I'm going to refer you to my book on random heterogeneous materials that has many references, but this was done well before my book. Okay. Now, I told you that hyperuniformity is going to be a useful new concept, and so I want to say a few words about that. This is not something that everybody knows about. It's not a household word, so I just want to give you a few slides about what is hyperuniformity. First, qualitatively. So a hyperuniform many-particle system is one in which large-scale density fluctuations are greatly suppressed compared to those of typical disordered systems like liquids. Turns out that all perfect crystals and all perfect quasicrystals are hyperuniform. Now, perfect crystals and quasicrystals have a special type of long-range order. So hyperuniformity, it turns out, provides a unified way of categorizing and characterizing crystals and quasicrystals. And then there are special disordered systems that have exactly the same character as perfect crystals and quasicrystals. They're hyperuniform, and they greatly suppress density fluctuations compared to typical garden variety disordered systems. So the disordered variety, it can be regarded to be new ideal states of disordered matter because they behave more like crystals or quasicrystals in the manner in which they suppress large-scale density fluctuations, and yet are also like liquids and glass since they're statistically isotropic structures with no Bragg peaks. They can exist as both equilibrium and non-equilibrium phases. They come in quantum mechanical and classical varieties, and they can be endowed with extraordinary bulk physical properties. So now, more quantitatively, what is hyperuniformity? Okay, so this was introduced in this rather abstract paper with Frank Stillinger in 2003, so 2 decades ago. And we were just interested in very basic questions concerning density fluctuations. So if you have points, say atoms or molecules of a liquid in d-dimensional space, we want to be able to, again, compute, in this case, the local number variance, because as I move this window from location to location here, the number of points within the window fluctuate. So we call this the number variance. Now, if you have a typical disordered system, like a Poisson point pattern, ideal gas, a typical liquid, this variance for large R scales like the volume of the window, the radius to the dimension. If you have a crystal, it scales like the radius to the d-1, which is the surface area of the window. And imagine now you have a disordered system, like this one here, that behaves just like the crystal at large scale. So it scales not like a typical system where the variance grows like the volume, but it scales like the surface area. Well, for large R, this is considerably much smaller than this. So that's what I mean by suppression of large-scale density fluctuations. And in particular, if it grows more slowly than the radius to the dimension, we call it hyperuniform. And that is actually also picked up by the structure factor, which you can get from scattering. And in particular, it means that the structure factor, the scattering intensity, goes to 0 as the wave number goes to 0. As I said, all perfect crystals and many perfect quasicrystals have this kind of scaling, surface area scaling. And in the case of the disordered variety, that means then you have a unified way of categorizing all of these different traditionally long-range order systems plus these exotic disordered ones. And so you can think of hyperuniformity as generalizing established notions of long-range order to include these special disordered states. Okay, now those are points. Now we want to be able to say, because we're interested in porous media, we really want the generalization of hyperuniformity to two-phase media. Okay, and that was done with a former student of mine, Chase Zachary. And again, we're measuring the local volume fraction fluctuations. And in this particular case, if you have garden variety disorder, the way it's defined, the volume fraction variance scales as 1 over the volume. It's just the definition of it. Now, if you have something that's hyperuniform, it goes faster than 1 over the volume. And that's equivalent to the spectral density tending to 0 as the wave number goes to 0 in the infinite wavelength limit. Okay. Now, here's 2D illustrations. I take in 2 dimensions, I'm going to multiply this variance by r squared. So if it is not hyperuniform, then for large enough r, this is going to asymptote to some constant value. If you have something that's hyperuniform, this function will actually continue to decrease. This is the corresponding non-hyperuniform spectral density, which you see does not go to 0, and the hyperuniform one, which does go to 0. The other point I want to make for anybody who's interested is that you can use the local volume fraction variance as an order metric to be able to characterize two-phase systems. And people actually have taken images using confocal microscopy of various types of media and have computed them, have computed the variance from digitized images. So this is a very easy thing to do. Okay, now let me talk about other general, more general scalings than the one that I just told you about. So let's consider that the spectral density has the power law behavior for hyperuniform systems as k goes to 0, k to the alpha, where alpha is some exponent. You can prove that you're in class 1 if that exponent is greater than 1. If it's exactly equal to 1, there's a logarithmic correction. And if it lies between 0 and 1, okay, which is the weakest form of hyperuniformity. So in other words, imagine when alpha is 0, then it's just the standard 1 over r to the d. That's the standard kind of non-hyperuniformity. But if alpha is between 0 and 1, you get class 3, which is the weakest form. This is the strongest form. And then there's an even stronger form that we call stealthy hyperuniform, which is also of class 1, where not only do you have the spectral density being 0 as k goes to 0, but it's actually 0 for a range of wave numbers around the origin. So these are very, very special exotic states. And I'm going to talk about later stealthy packings. So that's why I'm introducing that definition. Now, general non-hyperuniform scaling behaviors. Well, I've already told you the typical one. The typical one, the variance scales like 1 over the radius to the dimension. If you have alpha between less, that's negative, up to minus d, then we call these anti-hyperuniform. Okay, so that's even more slow than 1 over r to the d. And it turns out those would be, for example, some examples of the anti-hyperuniform ones would be fractal structures. So anti-hyperuniformity, so a fractal is exactly diametrically opposed to an hyperuniform system, because in one case, the spectral density is tending to 0. In the other case, it's tending to infinity. So you can use this, all of these, whether it's hyperuniform or not, to classify all translationally invariant states of matter according to their large-scale density fluctuations. Okay, now I want to just show you some examples of what the spectral density looks like for 3 types of hyperuniform sphere packings and 3 types of non-hyperuniform sphere packings. So in the case of a simple cubic packing, simple cubic lattice packing, you're going to get Bragg-like peaks that you hardly can see after the first Bragg peak. Okay, so that's what the spectral density looks like, where A is typically in this talk going to be the radius of the particle. Okay. And then you have what I'm going to call maximally random jam packings. So these would be if you take, say, marbles and you pack them into a container and you shook it up. Some people call it random close packing, and I'll tell you why we refer to this as maximally random jam packing. At some point, I'm going to give you some estimate of the fluid permeability of these packed beds. And here is an example of a stealthy packing. So you can see that this is the character of this is quite different than the character of this one, because here from 0 to up to this cutoff, spectral density is exactly 0. And here are 3 different non-hyperuniform sphere packings. You can think of them as sphere packings. This is, I'm going to call a Debye medium. This is really not a sphere packing. These 2 are sphere packings. This is overlapping spheres. So you put down spheres without any regard to whether they overlap. And you allow overlap. And you can see this is far from being hyperuniform. That's really what I want to emphasize. It's far from 0. Here's an equilibrium packing. So here you have correlated hard spheres, but not at jammed states. Okay. And so because it's not at a jam state, it is not going to 0 at the origin. By the way, does anybody have any questions? Or should I just save them for the end?
Actually, since you're asking, so when you look at the structure factor going to 0 and the Q equals 0, then I would think about the phase separation with a conserved order parameter. Then there you would see the structure factor. Is that then a hyperuniform state?
Yeah, that's a very interesting question, Per. So if you're talking about things like conheliad, spinodal decomposition.
Yes.
Yes. We have shown in a separate paper that actually is hyperuniform. I'm not going to say anything about that, but I thank you for that.
For old time's sakes.
Excuse me?
I'd like to see that for old time's sakes, if you could send me the reference.
Yeah, absolutely. Would you remind me in an email?
Yeah, no, I don't want to, because this is not something anybody else here knows about. So that would.
Absolutely. I'd be very happy to. By the way, I'm happy to entertain any kind of clarifying questions as I go along. So please feel free to interrupt me.
Okay. I wondered about the pore size distribution. You say at the limit of sort of delta equals 0, you get this specific surface divided by the porosity. I wonder why that is. So yeah, it was that last slide you were on.
Yeah, it's because, okay, you can think of because I'm asking for very, very small circles. You can imagine placing down circles of a given size. And because it's a probability density, I'm thinking about a differential element around the interface. Okay. And so that's why you end up picking up the specific surface, because when you make the probe particle, another way of thinking about the pore size probability is to think about the cumulative probability distribution that goes with it. And so that would be the probability that you throw a probe particle into your system of a given size and that it lands in the pore space. And as you make that probe particle smaller and smaller and smaller, it is going to pick up the information about the interface. Yeah. That's roughly what it is.
I'll give you a beautiful paper by Debye that actually George directed me to when I was a postdoc with him.
That'd be nice. Yeah, I like the probe
particle. I remember that pair.
Yeah.
Yep. That was a very nice paper.
It is.
So anyway, yeah, thank you for those questions. Anybody else? Okay. Oh, go ahead.
The density fluctuations that you're talking about to characterize these
Yes.
systems, there must be some time involved. Like, for example, a glass is a disordered state, but it is the density fluctuates very, very slow. How?
Well, no. Okay, so let me be clear about that, right? We yeah, of course, a glass, if you think about a glass in a kind of a dynamic way, we're thinking about taking snapshots of the glass, right? So you have a snapshot of the glass at some particular time. And so if you wanted to, you can probe structurally, spatially what's going on with the density fluctuations. And then you might, if you think about time, you might be taking snapshots later in time if the relaxation time is small. Usually, if you have a glass and you pass the glass transition, then the relaxation time is very, very large enough that you're not going to have to worry about any kind of dynamic changes. But, you know, the point is that regardless, what we're talking about here is taking snapshots of the system. And if you have, let's say, a large enough snapshot, you can get the information about the density fluctuations by probing that, or large enough windows, say, for a range of window sizes. Does that answer your question?
Yeah, thank you.
Okay. Yeah, thank you very much for these questions. It makes it much more interesting for me. Now I want to talk about, because I know Per says that a lot of you are interested in packed beds. So that actually is one of my specialties, packing problems. And so there's something that we call the maximally random jammed state. This is really different from random close packing that you might be familiar with, because random close packing is not very well defined mathematically. This was much a much firmer footing mathematically. And let me tell you roughly what it is. I have no time to really give you a talk about maximally random jammed states, but just to give you some flavor. You imagine that, first of all, the system is jammed. And what that really means is that I cannot compress the system. I cannot shear the system so that the particles start to fall apart, so that the bed falls apart. That's what I mean by strict jamming, okay? And it is maximally disordered according to certain order metrics that you can quantify the degree of order of the system. So among all jammed packings, which could be ordered, right? So you can have ordered packings like FCC. Among all possible jam packings, the one that has the highest degree of disorder is the maximally random jam state. And you can prove mathematically that if you had perfectly rigid hard spheres, that the moduli, the elastic moduli, would be infinite. Both the bulk and the shear modulus would be infinite. Now, it turns out that such packings have been shown to be hyperuniform. Okay, so this is something that's very, very easy to make, right, in the lab. And I'm sure that some of you are very, very familiar with this. First of all, does anybody have any questions on this point? Okay. So we're going to be interested in estimating the transport properties, including the fluid permeability of this very complicated pore space structure that this creates. All right, so now let me say something about NMR measurements. So as I mentioned earlier in the talk, the mean survival time I kind of already defined. I imagine that in the case of NMR relaxation times, I have, say, water molecules, and I put it in a magnetic field. So the protons are going to line up. I turn it off, and then the water molecules diffuse around, and you have paramagnetic impurities on the interface that then tend to demagnetize the particles. And if you have what's referred to as diffusion controlled reactions, whether it's diffusion controlled or not, I should say, you're interested in the mean survival time, the average time that it takes for a Brownian particle to survive before it gets trapped. And then you have the diffusion relaxation times, which describe the entire relaxation process and all of the relaxation times that go with it, where T1 I'm going to denote as the largest or principal relaxation time that determines the large time behavior, relaxation time of, let's say, the magnetization density. Now, in the case of conduction, I'm going to consider a porous medium. The pore space is filled with an electrically conducting fluid with this conductivity, and the solid phase is going to be perfectly insulating. Then I'm going to consider the dimensionless effective conductivity, the effective conductivity divided by the pore space conductivity. And the inverse of that, I call the formation factor. And that's going to be a measure of the tortuosity or the degree of windiness for electrical transport pathways in the pore space. And we're going to see that that's actually rigorously an important contribution to the fluid permeability. Now, in the case of Stokes flow and fluid permeability, of course, we have the fluid permeability, okay? But then we also have the so-called viscous relaxation times, which are associated with the Stokes time-dependent problem. So it would be the analogous quantities, except here we're having the Stokes problem, and here we have diffusion. So θ1 is I'm going to call it the viscous principal relaxation time. Okay. Now, in terms of the mean survival time, now I want to talk about rigorous bounds that involve the mean survival time. Now, the mean survival time, again, I want to emphasize, is going to be important for us to say something about the pore space statistics. And in particular, you can show that it's related to this length scale LP, where LP squared, the square of this length scale, is actually the integral of the spectral density, the one-dimensional integral of the spectral density. So this bound actually was derived by Prager, believe it or not. Well, no, sorry, I said that incorrectly. This bound actually was derived by me and Rubinstein in the 80s, and then in direct space. But then in this paper that I mentioned earlier in water resources, I showed that you can write it down in terms of the spectral density. So that's what I'm stating here. But anyway, this is a positive quantity. So all I'm doing is I'm just adding up this positive, I'm integrating over this positive quantity. It's actually bounded from below in terms of the mean pore size. So the mean survival time is greater than or equal to the square of the mean pore size. Now, the formation factor, again, I'm not going to have time to really describe this, but I just want to give you a flavor. The formation factor, there's a really good estimate that involves up to 4-point correlation function information. And it's given by this, where this is the volume fraction of the solid phase. And then zeta-2 and gamma-2, zeta-2 is a 3-point integral involving up to 3-point probability functions. And then this gamma-2 involves up to 4-point information. So these are functionals that involve, in particular, integrals over these quantities that I'm not going to describe. But the main point is that this is a very, very accurate predictor of the formation factor. Now, if you take the fluid permeability, interestingly, you can show that the fluid permeability is bounded from above by exactly the same length parameter that was involved in the mean survival time. Okay, so this is not a coincidence. It looks like it's a coincidence, but it's not. So that's why I say to you, it's very useful to be able to look at what are seemingly different properties and how they're actually related to the fluid permeability. Now, while this 2-point void bound, sometimes called the void bound, is not tight, admittedly not tight, it actually correctly ranks order the permeabilities of different models. And you can do that by looking at certain models for which we basically know the fluid permeability very, very precisely. Compute the bounds for exactly those same models, and then the rank order of the bound, and then the actual results coincide. Okay. Now, let me just say some key results from this paper. So you can use this 2-point void upper bound in the way I just described, right? And then you can ascertain how the permeabilities of the hyperuniform ones behave compared to the non-hyperuniform ones. So we're going to use this 2-point bound to be able to at least qualitatively say what is going on. What do we learn about hyperuniform porous media versus non-hyperuniform? Okay. Now I found that the velocity fields in the non-hyperuniform porous media are generally much more localized over the pore space compared to those in the hyperuniform counterparts, which implies that the former is going to have higher permeabilities than the latter because of the localization. So here are images of the pore space for non-hyperuniform and hyperuniform porous media. This one is non-hyperuniform, okay? And you can see that this is the pore space. You can see how localized it is. And here is a weakly hyperuniform case. And here is a strongly hyperuniform case. Strongly in this case means these stealthy systems. And you can see how the pore space is really very uniformly distributed in the entire volume. So greater delocalization results in greater variability in the geometry of the pore channels and hence lower permeabilities. So you might be able to say that you could use these kinds of principles to design disordered porous materials with desirable transport properties.
Excuse me,
Yes.
I think so, but the pore space is percolating in all these cases, right?
Absolutely. Yes. Absolutely. Yeah, and in fact, just to add to that, what I said to you was I was showing you the pore space. Well, what I have done is I purposely have dilated the solid phase so that it would be easier to visualize the pore space. So in fact, the actual pore space is larger than what I'm presenting.
Oh.
Excuse me, Salvatore.
Sure.
To me, it seems like when you talk about this hyperuniform, it's almost like you're zooming out and in more of an RV scale. But
I didn't get that last phrase.
when you're talking about this hyperuniform, to me it seems like you in some sense are zooming out, that you were getting a more homogeneous medium and you are more on a representative elementary volume, as some will call it. But I guess you are talking more on the structure, right? Than
yes. So I want to focus on the word you used, assuming. We're not assuming anything. You can think of it as a categorization. So in other words, it's either a property of the system, structural property of the system, or it's not. And you can create them. And I'm not going to have any time to tell you how you could create them. But if you take a system, it's either going to be hyperuniform or not be hyperuniform. There's no assumption about anything. So if I do have something that is stealthy hyperuniform, which is what this example, can you see my cursor?
Yes.
Yes. Then this is actually a consequence of the fact that I started with that system.
Mm-hmm.
So suppose you take the left figure there, the non-hyperuniform figure.
Yes. Yes.
Put many of those blocks next to each other. then you will get a picture that looks pretty much like the figure on the right.
Yes, absolutely. But don't forget, very, very important point. Good. That's an excellent point. You always have to talk about, in the case of hyperuniformity, technically, you're talking about an infinite system limit.
Mhm.
And if you think about a periodic system, you can think about, and this is what we always do when we simulate a disordered system, like an equilibrium hard sphere system on the computer, we use periodic boundary conditions. And therefore, you actually have a periodic approximate of a disordered system. But if the correlation length in that system is small compared to the system size, then you're okay, right? So this is always done.
Right.
Right?
Yeah.
Thank you.
Yeah, sure. Now, if I can, now I want to present a relation that you might not be familiar with. So anybody who doesn't know about this, I would really love to be able to talk about this because this is something that may not be known. You can actually write down the exact expression for the fluid permeability. This is it. And this length is a parameter that is a sum over the viscous relaxation time. So it's exact. And it comes from the Stokes operator. So it comes from the eigenvalue problem for the Stokes operator. So that's a very precise statement. And in the denominator, we have the formation factor. Now you might ask, why do we have 8 here? Well, that's a matter of definition, and we wanted to make contact with tubes. But in fact, you could absorb the 8 into this, okay? You just have a length scale squared divided by the formation factor. Now, again, I'm showing you a flow in a porous medium, in this case 2D. And the important thing that I think everybody in this audience knows is that only some parts of the pore space are really going to be, I'm going to call it, dynamically connected. In other words, certain portions of the porous medium will have significant flow and other portions will not, okay? And so estimates that just are purely based upon simple microstructural parameters like the porosity itself and just the specific surface are not going to capture good estimates, not going to be very predictive. So you want, and so F, what does F do? F measures kind of tortuosity that you have, the windiness. Doesn't tell you about the dynamically connected part or not. This L parameter does. So if you're gonna estimate the fluid permeability, this is telling you, you know, how you have to go about it, right? At least physically what's involved in it. Now, there are rigorous bounds on the fluid permeability in terms of the diffusion parameters. So these are called cross-property bounds. So it's one thing to say that the fluid permeability should somehow be related to diffusion parameters. It's another thing then to derive it and prove it. So you can actually show that these diffusion parameters are linked to the fluid permeability by rigorous bounds. In particular, you can show that if you have the mean survival time, you have an upper bound on the fluid permeability. Now, in general, this upper bound is not extremely tight. A better bound involves taking the relaxation time, principal relaxation time, and dividing it by the formation factor. That does better than this one. Now I'm going to skip a lot of material. For those of you who want to know more about it, you can go to this article in Advances in Water Resources. And I propose the following approximation that does fairly well. And I'm going to show you what that means in a second. I'm taking the second moment of the pore size and I divide it by the formation factor, okay? And that's going to give me a pretty good approximation of the fluid permeability. And here is a prediction. So we have exact data for the fluid permeability, essentially exact. done by Sangani and Akrivos a long time ago for BCC, the body-centered cubic. We can then compute the mean pore size, or the second moment, for the same exact model, and compare the prediction of that formula to the data. And you can see that it falls very, very closely to the data, right? Now, given that this is that accurate, then I could try to see what happens when we have equilibrium packings of spheres. So this is the red curve here. And then you have the stealthy packings, okay? And then you have the BCC as a comparison. And as expected, because the equilibrium hard spheres involve a more localized pore space, it's going to have a higher fluid permeability. Equilibrium hard spheres, you imagine they're undergoing collisions, they're in equilibrium, and I'll be happy to tell you in more detail what that is if anybody has questions. But this is just to give you an idea of the accuracy of the prediction. So the moral of the story is having the pore statistics, having the pore space probability density function or its cumulative probability distribution, which is probably easier to measure. And then you can take a derivative of that to get the probability density if you like. Turns out to have very, very useful information. But you also need the formation factor. Okay, now I'm going to take the MRJ sphere packing that I showed you earlier, and I'm going to apply the formula to this. And when I make the permeability dimensionless with the radius squared of the particle, this is the fluid permeability, 0.01 at this porosity. And I'm going to compare that to the BCC packing, which is about an order of magnitude less. Okay, so this is all consistent with the qualitative picture that I laid out before. Okay, now I'm going to move to the second part of the talk, and I'm going to tell you about a result, an obscure result due to Prager from 1963 that had about, I don't know, at the time that I had written a paper about that extended this work, it had about maybe 5 or 6 citations. So it was completely ignored. So let me tell you what the problem is. I have a two-phase system, okay? And I imagine that I have some solute particles that start out initially all in one particular phase. And I'm going to call this the particle phase. This is just a cartoon. And it's completely absent from the other phase at time is equal to 0. Then I release it. I release the diffusing particles, and then I watch how that solute species diffuses into the other phase. And if I wait, and then what I'm interested in is the fraction of total amount of solute present that is diffused into phase 1 at time t. I'm going to call that the spreadability, script S of t. And of course, at infinite time, then it uniformly, the diffusing species uniformly fills the entire system. Okay, now Prager recognized the problem can be solved exactly just in terms of the 2-point probability function that I mentioned to you earlier. And he did this, he wrote his solution down in 3D. Now, this is very, very interesting because there are very few two-phase media problems where everything is determined entirely by 2-point statistics. And as I said, this result, the significance of this result was largely ignored for 60 years. Okay, so in this paper, in Physical Review E, I generalized his expression to any dimension and obtained a Fourier representation, which turns out to be very, very powerful. You could actually obtain exact series representations for any model. You could look at the short time and long time behaviors you could show that the short time behavior is linked to the small scale structure behavior. The long time behavior is linked to the large scale structure. You can look at consequences for hyperuniform, non-hyperuniform media. You could apply it to many particle packing examples. And then the more very, very interesting thing is that you can relate this. I related this to NMR pulse field gradient spin echo amplitude and diffusion MRI measurements, which sounds very, very crazy, but it's true. And then you can actually relate these problems to very pure mathematics problems in discrete geometry. Okay, so let's begin with the generalization of that d-dimensional formula of his Prager's formula in any space dimension. And I'm going to call this S infinity, where S infinity is phi1, because then everything goes into the fraction is at infinite time is just the porosity, say. Minus this, I'm going to call that the excess spreadability. Now you can show using Parseval's theorem that immediately you have a Fourier representation in terms of the spectral density. And therefore, because of the nature of this function, this is positive. So you can't tell from this direct space representation what's going on, but here it's very easy. This is always positive. So this comes from the Green's function of the diffusion operator. This is always positive. So everything here has to be, the integrand is positive. So the short, intermediate, and long time behaviors of the spreadability is linked directly to the small, intermediate, and large scale structural characteristics via these 2-point statistics. And you can do it exactly for general microstructure. So that's a beautiful capacity to have that. And the long time behavior of the spreadability is an accurate way to extract the exponent alpha that I showed you earlier when you have a power law spectral density as k goes to 0. Okay. Now here what I'm showing is 3D microstructures with various symmetries. So you might say, well, what does 1D mean? Well, 1D means you have stratified media. So you can show that in one dimension, it's exactly equivalent to 3-dimensional stratified media. And in 2 dimensions, the result d is equal to 2 corresponds to systems in which you have transverse isotropy. And then, of course, in the case of fully isotropic 3-dimensional structures, you have these examples. Now, the ones on the left are non-hyperuniform, these blue ones. The ones in green are actually all hyperuniform ones. Okay. Now, in particular, the short time behavior, I told you that it's connected to small scale. Well, in particular, if you have the small time exact asymptotic expansion, it's given by this. Well, that's determined by the small r expansion of the autocovariance function. And because of that, then the leading order term in the small time expansion of the spreadability is directly related to the specific surface. Well, that's not surprising because at very, very small time, all you're doing is you're going out beyond I showed you that cartoon of particles. You're just going out a really tiny distance. And so you're picking up the information about the interface. And then this thing proportional to time involves this coefficient that's in the small r expansion of the autocovariance function. So again, you can see how small scale, small times are connected to each other. Now, if you have, again, this power law scaling that I referred to earlier, but now I'm putting in the dimensional quantities and the coefficient b, then you can show that for any system, the large time behavior of the spreadability is given by this exact form where the d is the dimension, alpha is the exponent here. And then you can see that everything is controlled by the exponent, d to the plus alpha. So if I plot this as a function of time, just like I would magnetization density as a function of time, and I look at the long time behavior, from that, I could extract alpha, which is a measure of the large scale fluctuations. And therefore, it tells us that everything is determined by this exponent. So if alpha is becoming large, which means it's going to be hyperuniform, it's going to go decay faster. If it becomes smaller, it's to decay more slowly. Okay. And then if it's actually stealthy, you can show that it's no longer power law. It actually decays even faster. It becomes exponentially fast. Okay. So if you have a disordered stealthy hyperuniform sphere packing, then you can show that the spreadability has this particular form. And this is the cutoff K, where the spectral density, remember I said, is 0 up to that cutoff. And this is exactly the form. You get this exponential kind of behavior. So that's much faster than the power law that I showed you. And if you have a periodic packing, everything is determined by the first Bragg peak. And if you want to know which one has the fastest among all periodic packings, it's the one that has the smallest positive Q1. And in dimension one, it's the integer lattice. In dimension 2, it's the triangular lattice. In dimension 3, BCC is going to have the fastest among all periodic structures. And then you can actually say something about what happens in higher dimensions, which I'm not going to bore you with. But the moral of the story is it's useful to have these benchmark examples, because you at least know what's the fastest possible times you can have. And you could use that as a guide compared to, let's say, something that's more typical, disordered. Okay, so in the case of the spreadability, then you have a phase diagram, right? And I'm going to show you. So alpha takes on values between minus d, so the minus is cut off there, minus d to plus infinity. If alpha is to the left, you're in the non-hyperuniform regime. And in particular, if it's typical non-hyperuniform, then it goes like d to the minus d over 2. But if it's stronger and it's anti-hyperuniform, then it goes like this, okay? Which is much slower than this. If you're to the right, then you're in the hyperuniform regime. And if you have typical hyperuniform, you have inverse power law, where alpha is, as I said, it's going to be greater than 0. So you're going to be in a certain hyperuniformity class. And then if it's stealthy hyperuniform, it's this exponential decay. So here's just an example of what it looks like for 3 models. I'm showing an anti-hyperuniform medium, a Debye medium, which is typical non-hyperuniform, and then a hyperuniform one, right? And so this is the large time behavior. And so from this large time behavior on this log-log plot, you can read off what the slope is. In this case, 5/2. In this case, 3/2. In this case, I can't give you the exact number because it's cut off. It looks like it's just linear. Anyway, so that's the moral of the story, right? So you can read it off from here. And I'll skip this. I'll tell you that this problem is actually connected to what's called the covering problem in discrete geometry, which is a very important problem in pure mathematics. And the covering problem asks for the point configuration that minimizes the radius of overlapping spheres, circumscribed around each of the points required to cover d-dimensional Euclidean space. So covering means that I actually have to have overlap. But certain arrangements will give you a more efficient covering than others, okay? And it turns out that the winners that I just showed you for the spreadability are exactly the same winners as for the covering problem. So there's a beautiful connection to pure mathematics. Then I want to point out that there is an amazing set of results that were done by Pavitra Sen and his collaborators from Schlumberger Dahl from the 80s and 90s that involve NMR relaxation. And I want to just make the connection to this. So again, let's consider a fluid saturated porous medium with paramagnetic impurities at the interface. The quantity m of q of t is the NMR pulse field gradient spin echo amplitude, which depends on the wave vector q and time t. And it's been known that that contains information on both the spectrum and eigenfunctions of the diffusion operator, which are determined by the microstructure. So what they did was they came up with an effective diffusion propagator to obtain an accurate approximation for this m of q of t. Now, I noticed that if you set that wave vector equal to q, it gives in their formulation the total magnetization as a function of time that is this. Well, if you remember what I showed you earlier, this is almost exactly the same form as the spreadability. In fact, you can map the spreadability problem to this effective diffusion propagator picture by saying this excess spreadability is this magnetization at q is equal to 0. And you replace my d, which is a constant diffusion for the solute species, with the time-dependent diffusion, and you notice that at time going to infinity, this is nothing more than the effective diffusion coefficient. This is exactly the same form as the spreadability. And then I want to mention that Novikov et al. Used simple 1D models to find the same type of long-time scaling for the time-dependent diffusion, for diffusion-weighted MRI, exactly in the same way as I did for the spreadability. So there's these beautiful connections, so that even though it appears that the spreadability is this abstract quantity, it actually has direct connections to NMR relaxation, and therefore you could use it to actually make measurements. And we have used it, for example, in the case of sandstone, to make predictions about what the spreadability is for sandstone. And with that, I want to just tell you, summarize conclusions. So rigorous bounds on transport properties of porous media that depend on microstructural information provide useful property estimates. The cross-property relations that link diffusion properties to the fluid permeability can yield good estimates of the latter. Ordered and disordered hyperuniform porous media, including particle packings, are endowed with unique transport properties that we are only beginning to discover. Because the pore space in stealthy hyperuniform porous media is highly delocalized, the entire pore space is more uniformly dynamically connected, leading to lower permeabilities than their non-hyperuniform counterparts. Spreadability of diffusion information across timescales is a powerful tool to dynamically probe and classify all translationally invariant two-phase microstructures across length scales. And we identified a remarkable connection between spreadability and non-invasive NMR measurements in physical and biological porous media. And finally, I believe these general findings, all of these parts of the talk, have implications for the design of porous materials with desired transport properties, because you can use the known microstructure dependence to be able to then tune the particular transport properties. Thank you for your attention.